Today's webinar speaker is Allison, who is a SIG postdoc here at UC Davis. Callie received her PhD at Stanford University. Her postdoc here, as well as at University of Maryland, continues her thesis work and interest in earthquake cycle modeling. Today, her talk, Interaction Between Earthquakes and Interseismic Deformation, will review the state of the earthquake cycle modeling and explore simple and implications of more complex models. The screen is yours.
Great. In this talk, I'll start by presenting some background material about different approaches to modeling earthquakes and how they can contribute to our understanding of seismic hazard. These approaches fall broadly into three categories: single dynamic rupture simulations, earthquake cycle simulations, and earthquake simulators. After that, I'll go into my research, which focuses on earthquake cycle models, starting with the mechanics of the simplest cycle model that features both spontaneous earthquakes and a shear zone with viscoelastic deformation. Then I'll talk about my work developing and implementing an algorithm to incorporate inertia and wave propagation into the coseismic phase of my model. And finally, I'll discuss my work incorporating two different weakening mechanisms which may be active in the shear zone: shear heating and grain size reduction. This is a snapshot of the shaking intensity predicted by a shakeout scenario magnitude 7.8 earthquake on the San Andreas in Southern California, which was put together as part of an earthquake preparedness campaign in 2008. The fault is shown in pink here in the middle. North is pointing to the left, and the color shows shaking intensity, with dark red indicating the highest shaking intensity. This scenario used a simple kinematic model for the earthquake, meaning that the epicenter of the earthquake, the rupture velocity, and the portion of the fault which slips are all assumed. The model might be improved using a physics-based approach to modeling the earthquake source. These physics-based earthquake models can be divided to three categories, which I've depicted here in this diagram, with model time and number of earthquakes increasing from left to right. Single dynamic rupture simulations, on the far left, model a single earthquake and focus on the physics of the rupture processes. Earthquake cycle simulations model a sequence of earthquakes over a 1,000-year timescale and seek to model both the rupture processes and interseismic processes. To achieve these longer timescales, earthquake cycle simulations typically include fewer physical processes during the earthquake, particularly ground motion physics, compared with single dynamic rupture simulations. It's also a newer field, so most studies that have been done focus on understanding the effects of a particular physical mechanism or multiple mechanisms, and as a result, use a more simplified fault geometry, often working in 2D. At the far right, earthquake simulators cover the longest time range, around 1 million years. They produce a catalog of earthquakes over this very long time frame, seeking to characterize the system-level response of a complex network of faults over a large region, such as the major faults in the entire state of California. To achieve this, they make a number of simplifications to the earthquake and interseismic processes. Earthquake simulator is the official name for this category, but a more complete name might be earthquake catalog simulator. Next, I'll provide an overview of some of the findings from each category of model. Here I'm showing results from a study on the effect of a fractally rough fault on a dynamic rupture. Dunham et al. 2011 found that ruptures are sensitive to fault roughness, and that fault roughness produces accelerations and decelerations of the rupture, which, together with the naturally emerging slip heterogeneity, excites more high-frequency waves than a smooth fault, resulting in ground acceleration spectra that are more consistent with strong motion records. Here's another example of a single dynamic rupture simulation. Bidlin et al. 2017 performed simulations to mimic recorded earthquakes in a target region in Oklahoma and Kansas. They use these simulations to augment the recorded event data, providing more data with a short source to site distance. They combine the recorded and the synthetic ground motion data to produce a composite ground motion catalog. In the figure shown here, the recorded data is in gray and the simulated data is in green. And finally, they use this catalog to develop a region-specific GMPE for the target region. At the other end of the spectrum, from single dynamic ruptures, earthquake catalog simulators like RSQSim simulate a large catalog of earthquakes on a complex network of faults over a very long time frame. This catalog of earthquakes is then fed into statistical ground motion models to produce shaking levels for individual events and ultimately to estimate hazard. This figure compares RSQSim's hazard estimate on the right with USURF3 on the left. The maps both show the peak level of ground acceleration expected to be exceeded at the 2% probability level over a 50-year time period, expressed as a fraction of the acceleration of gravity. To accomplish this, RSQSim makes a number of approximations, such as radically simplifying fault frictional behavior, assuming a constant slip rate during rupture, and loading the faults using a backslip method that fixes the fault slip to a specified rate during the interseismic period. The dynamic rupture component of RSQSim has been validated against fully dynamic rupture simulations. However, the interseismic component has yet to be validated. This is something that earthquake cycle simulations would be uniquely positioned to do. Like earthquake simulators, earthquake cycle simulations model both the earthquakes and the interseismic period, but they make fewer simplifying assumptions to the physics. The idea is to have one physical model that resolves the physics of slow tectonic loading, earthquake nucleation, rupture propagation, and transient coseismic deformation. This figure is from Barbeau et al.'s 2012 paper, Under the Hood of the Earthquake Machine, toward predictive modeling of the seismic cycle. Here they model the Parkfield segment of the San Andreas Fault and reproduce a realistic earthquake sequence that includes events similar to those that occurred in 1966 and 2004. They are also able to match interseismic, coseismic, and post-seismic observations. This is a video showing earthquake cycle simulation from the code used in that 2012 paper. This video is from a 2016 paper by Junli Zhang and Nadia Lapusta. In the video, we're looking head-on at a strike-slip fault. This white dashed box in the middle indicates where properties on the fault have been changed. Inside the box, the fault will host earthquakes, and outside the box, it will instead host aseismic slip. The color indicates the slip velocity on the fault. I think I'll start the video while I talk here. So the color indicates the slip velocity on the fault. Where it's dark blue, it's slipping aseismically at the tectonic plate velocity, and where it's black, it's effectively locked. As the video plays, this aseismic slip produces microseismic events. Those are these small circles that are popping off with brighter colors. That was the nucleation of the large event. So eventually, the fault creep at depth has loaded the locked portion of the fault, and a major earthquake occurred. In the first few months to years after the earthquake, the slip velocity on the fault is temporarily elevated in a process called frictional afterslip, and the rate of microseismicity is also elevated. Let me see if I can back this up so you can watch that earthquake nucleate again, because I know it goes by really quickly. Zhang and Lapusta used this model to investigate the relationship between large earthquakes and microseismicity. They suggest that the absence of concentrated microseismicity on a fault indicates deep rupture past the seismogenic zone in previous large earthquakes. They used this model to investigate the relationship between microseismicity and the down-dip propagation limit of large earthquakes. They suggest that the absence of concentrated microseismicity on the section of the San Andreas, which ruptured in the 1857 Tejon Pass earthquake, highlighted in red on the top figure, indicates that this earthquake penetrated at least 3 to 5 kilometers below the seismogenic zone, which deepened the locked to creeping transition on these segments and suppressed and continues to suppress microseismicity. This is another example of an earthquake cycle simulation, in this case examining the effects of off-fault heterogeneity. Erickson and Dunham, 2014, consider a vertical strike-slip fault cutting through an elliptic sedimentary basin of depth D and width W. The basin has much lower shear modulus than the surrounding material. They find that a simple model without the basin produces a sequence of identical earthquakes that rupture the entire seismogenic zone of the fault. However, when a basin of sufficiently low shear modulus is present, it can introduce complexity, producing earthquakes that do not propagate all the way through the basin, or subbasin events, and larger earthquakes that do propagate through the basin. And finally, this is another example of an earthquake cycle simulation, in this case including fluid flow along a fault into earthquake cycle simulations. Weicheng Zhu incorporated pore pressure evolution and fault valving, cyclic changes in pressure and unsteady fluid migration along faults into Maya 2D earthquake cycle code. Coupling between fluid flow, fault slip, and pressure evolution produces fluid-driven aseismic slip near the base of the seismogenic zone and earthquake swarms within the seismogenic zone. So in summary, there are 3 categories of approach to modeling earthquakes, which plays a critical role in evaluating seismic hazard. I've chosen to focus on earthquake cycle simulations in my work to explore the interaction between earthquakes and interseismic processes such as aseismic fault slip and bulk viscous flow. In contrast with single dynamic rupture simulations, earthquakes spontaneously nucleate in earthquake cycle simulations. They don't have to be forced. Additionally, after an initial spin-up period, earthquake cycle simulations have no dependence on initial conditions and instead become self-consistent. Similarly, the simplifying assumptions made by earthquake simulators make them ill-suited to studying interseismic physical processes in detail. So now I'm going to shift to talking about my work on earthquake cycle simulations with viscoelasticity. This section is work that I did during my PhD at Stanford. Observations of earthquakes on strike-slip faults can be conceptualized into two end-member models of different transitions in deformation at depth, both resulting from the increase in temperature with depth. In model 1, the transition is in the deformation style of the fault. The shallow portion of the fault is unstable and can host earthquakes, while the deeper portion creeps stably and does not permit earthquakes. In model 2, the transition is in the deformation style of the off-fault material. In the shallow crust, deformation is highly localized, so a fault capable of hosting earthquakes exists. Deeper down, the higher temperature allow the off-fault material to flow, and deformation becomes more distributed and the fault ceases to exist. Most previous earthquake cycle work, including all the examples that I just went through, have taken the form of the first model, which is the simplest physics-based model to include both interseismic loading and spontaneously generated earthquakes. In my work, I add model 2 to this, so the fault is loaded by both aseismic slip and by distributed off-fault deformation at depth. This is a schematic of my model. I've chosen a very simple geometry to focus on the interaction between the fault and the off-fault material. The model is of a vertical strike-slip fault in 2D. The fault cuts through the middle of the domain, so it's this part right here, and it persists all the way to the base of the model. The fault is governed by rate and state friction. The shallow portion of the fault is velocity weakening and hosts earthquakes, and the deeper portion is velocity strengthening and is able to slip aseismically. Earthquakes will nucleate at the velocity weakening to velocity strengthening transition. The off-fault material is represented with the power law of viscoelastic rheology, using parameters for wet feldspar in the crust down to 30 kilometers depth and parameters for wet olivine in the mantle below that. In the shallow crust, it will behave as effectively elastic, while deeper in the domain, it will be weaker and deform ductily. The brittle-ductile transition will evolve naturally out of the model rather than being imposed and may not occur at the same depth as the velocity weakening to velocity strengthening transition. Oh, sorry, I have a visitor here. The model will be loaded through the displacement of the remote boundaries at the left and the right here at the tectonic loading velocity of 32 millimeters per year, or 10 to the minus 9 meters per second. It's this remote displacement that will drive aseismic fault slip and bulk viscous flow at depth and ultimately earthquakes. The interaction between friction and viscoelasticity can be understood by plotting their respective strengths. Here I'm plotting a sampled geotherm on the far left, and second, the rate and state frictional properties of the fault as a function of depth, which are based on experimental results from Blampede et al. In 1995. The velocity weakening to velocity strengthening transition occurs here at about 15 kilometers. The third plot is the effective viscosity for this geotherm, assuming a constant reference strain rate of 10 to the minus 14 meters per second. The effective viscosity decreases rapidly with depth due to its exponential dependence on temperature. The far right figure shows the strength of the frictional fault in yellow and the strength of the off-fault material in blue. The viscous strength of the off-fault material is very high in the uppermost crust, where the viscosity is high, and is very low at depth where the viscosity is low. So in the uppermost crust, the fault is much weaker than the off-fault material, and so the fault will be what deforms in response to tectonic plate motion, and friction will dominate the behavior of the system. Deeper down, the viscous strength is much lower than the frictional strength, so the dominant deformation mechanism will be bulk viscous flow. The transition zone, where both deformation mechanisms are of similar importance, is called the brittle-ductile transition. This model of the Earth is called the creme brulee model because it consists of a strong, brittle upper layer overlaying a weak layer that is able to flow. This is an example of a viscoelastic earthquake cycle simulation using my model. Here I'm plotting shear stress on the fault over time, where time is on the x-axis and depth along the fault is on the y-axis. The discontinuities that you see are the earthquakes, which take place over about 30 seconds and thus are too short to be visible in the plot, but their effect on the stress is clearly visible. During the interseismic period, a stress concentration builds up at the transition between the velocity weakening and velocity strengthening portion of the fault. The concentration gradually builds in amplitude and moves up the fault until it nucleates an earthquake. In this simulation, the stress concentration actually produces a slow slip event first, which releases some of the stress on the fault, and then a new stress concentration develops, which produces the earthquake. To illustrate how the remote tectonic motion loads the fault, I've plotted the slip velocity on the fault on the top. In this plot, white represents when the fault is slipping at exactly the tectonic plate velocity of 10 to the minus 9 meters per second, or 35 millimeters per year. If the whole fault was moving at that velocity, then no stress would build up and there would be no earthquakes. Blue represents velocities below 35 millimeters per year, with dark blue meaning the fault is effectively locked, as it is in much of the upper crust in the interseismic periods. So the fault is creeping at approximately the tectonic loading velocity from 15 to 20 kilometers, so in this region here, while the upper portion of the fault is locked. That causes the stress concentration to build up that's visible in the lower shear stress plot. Just looking at this plot, you'd get the impression that the fault is locked below 20 kilometers, but actually that's where the off-fault material is much weaker than the frictional strength of the fault, and thus where bulk viscous deformation is occurring instead. These are snapshots of the accumulated viscous strain on the top row and the viscous strain rate on the bottom row for one interseismic period. This model is symmetric around the fault, so I'm showing cross sections on the right side of the domain with the fault on the left edge of the figure. The viscous strain rate is elevated at the beginning of the interseismic period and gradually decreases through the interseismic period. The peak of the viscous strain occurs at about the depth where the fault ceases to slip aseismically, that's right around here. In this example, it's about 22 kilometers, and the shear zone widens below this point. This plot on the right is a zoom in on the earthquake over 25 seconds. The earthquake nucleates right here, and then the ruptures propagate up and down the fault at the shear wave speed. When the upgoing rupture tip reaches the Earth's surface, it's reflected. The downgoing rupture tip begins to slow as it reaches the velocity strengthening portion of the fault. It gets a little kick from the reflection of the upgoing rupture tip. And I'd like to stop here and take questions about this particular simulation before I go on to complicate it. Okay. Oh, all right. So finally, this is a comparison between my viscoelastic cycle simulation on the bottom and an equivalent elastic cycle simulation on the top. In the elastic simulation, a seismic slip on the fault occurs everywhere below the seismogenic zone. The recurrence interval in both simulations is 270 years, and the earthquakes are the same size. So the difference in deformation in the lower crust between these two simulations does not lead to a difference in the behavior of the seismogenic zone. Although I've only shown one example, I considered a range of geotherms such that the simulations I considered spanned a range of effective viscosity estimates for the Western US. I found that the predicted lower crustal deformation mechanism ranged from significant interseismic fault slip to purely bulk viscous flow. However, the earthquake cycle characteristics, such as the recurrence interval, the nucleation depth, and the down dip limit of slip were almost identical. Next, I'll talk about work that I did to include full inertia and wave propagation in my code. The previous results were performed with an approximation to inertia called the quasi-dynamic approximation during the earthquakes. Kenneth Duru, an applied mathematician at Australia National University, Eric Dunham, and I developed and implemented an algorithm that incorporates full inertia and wave propagation during the earthquakes. The new and improved algorithm produces more accurate earthquakes and is actually much faster. This is because now during the earthquakes, each time step only requires a matrix vector multiplication rather than the solution of a linear system. The interseismic period still requires the solution of that linear system, and it represents a significant challenge as the cycle modeling community seeks to move to 3D. The elastic wave equation, which is solved during earthquakes, is hyperbolic, and hyperbolic systems are relatively well studied. So as a community, we understand how to produce good scaling and take advantage of high performance computing resources. The interseismic period, however, involves solving an elliptic equation, which is relatively less well studied and is quite challenging to solve efficiently. I'm currently working with Kenneth Duru and Linda Stalls, also an applied mathematician at Australia National University, to improve the performance of this step, the long-term goal of rendering 3D problems more tractable. Next, I'll talk about work that I did incorporating weakening mechanisms which may be active in shear zones into my earthquake cycle modeling. And I'll start with shear heating. In addition to considering the effects of shear heating, I also explore the dependence of the brittle-ductile transition in the earthquake cycle on the background geotherm. I consider a range of background geotherms parameterized with the lithosphere asthenosphere depth, the LAB depth, I set the temperature at the Earth's surface to 10 degrees Celsius, impose an adiabat in the asthenosphere, this is the green line here, and define the LAB depth as the intersection between the conductive geotherm and the adiabat. I'll consider a range of LAB depths from 40 kilometers, the warmest geotherm, shown in red, to 70 kilometers, the coolest in purple. This range of geotherms produces surface heat flows, which is generally representative of the range seen in Southern California. The figure on the left here shows the geotherms, and the figure on the right shows the average interseismic shear stress on the fault resulting from cycle simulations run with these geotherms. In general, warmer geotherms leads to a weaker lower crust and upper mantle. These plots show the structure of a shear zone as a function of depth on the y-axis and distance from the fault on the x-axis. The contours show the deviatoric strain rate, with dark purple corresponding to the highest strain rates and white to the lowest. Looking at the figure on the left, the shear zone starts in the lower crust and becomes broader with depth. Define the brittle-ductile transition as the depth range over which the fault accommodates 10% to 90% of tectonic plate motion. The figure on the left is for a warmer geotherm, and the figure on the right is for a cooler geotherm. The warmer geotherm leads to a shallower BDT, indicated with a gray box. And as a result, the shear zone initiates at a much shallower depth in the lower crust, whereas on the right, the BDT occurs below the moho. The red line indicates the down dip limit of the earthquakes in the model. In both cases, the earthquakes propagate down to 16 kilometers, which results from the velocity weakening to velocity strengthening transition that I've built into the fault. In these simulations, I held that velocity weakening to velocity strengthening transition at a constant depth corresponding to an intermediate geotherm rather than allowing it to vary with the background geotherm. And that was to make the analysis simpler. This range of structure is observed for strike slip faults. For example, some of the Marlborough faults in New Zealand appear to end in distributed deformation in the lower crust. And the San Jacinto fault in Southern California appears to persist as a localized feature down to the moho. These faults don't have the same age or geologic setting, so I don't want to imply that geotherm is the only parameter that can explain this range of fault and shear zone structures. But I do want to highlight that temperature plays a major role in determining the depth of the brittle-ductile transition and therefore the structure of a strike slip fault in its shear zone. Having highlighted the importance of temperature, I will now add heat generation to the model in the form of shear heating. There are two sources of shear heating. Frictional shear heating is the generation of heat through motion on the fault surface. So that would be if you're pushing your hands together to generate heat. If you push harder, you generate more heat. Viscous shear heating is the distributed equivalent, the generation of heat through bulk viscous flow. With shear heating, frictional and viscous dissipation generate heat, and this increases the temperature. The increase in temperature decreases the effective viscosity, which in turn causes the viscous strain rates and stresses to change, which changes the amount of heat generated through frictional and viscous dissipation. So shear heating results in a fully coupled system between the momentum balance equation and the diffusion equation for temperature. And in my model, I'm spreading frictional shear heating out over a Gaussian half-width W because without dynamic weakening on the fault, rate and state friction produces hugely unrealistic temperature changes. The effect of shear heating is to produce a temperature rise or a thermal anomaly on top of the background geotherm. The results plotted here are for the same viscoelastic simulation that I showed earlier with shear heating turned on. I've plotted the average interseismic temperature rise on the right. It peaks in the mid crust at 170 degrees Celsius. This thermal anomaly weakens the root of the fault and produces a much shallower brittle-ductile transition. In this example, it shallows the BDT by almost 10 kilometers. The thermal anomaly is time dependent since each earthquake dumps out heat through frictional shear heating, which then diffuses away during the interseismic period. These are snapshots of the resulting transient temperature rise through the interseismic period for this simulation from 1 day after the earthquake to 1 year. The top 4 plots are all zoomed in to within 10 meters of the fault, with the y-axis going from 0 to 30 kilometers. And then the bottom plot shows the average interseismic thermal anomaly zoomed out to 30 kilometers from the fault. So what's happening here is the heat generated from the earthquake, which results in a significant temperature rise that's initially concentrated to within 1 meter of the fault. This gradually diffuses and becomes negligible by 1 year after the earthquake. It is diffusing, you can see it diffusing easily in the horizontal direction in these images. It is diffusing in the vertical direction as well, but that axis is zoomed out to 30 kilometers, so you just don't see it moving in the figure. The temperature rise depends on the frictional shear zone width. This is a plot of maximum temperature rise for an entire cycle, plotted as a function of the frictional shear zone width that I'm imposing in the model. Decreasing the width of the shear zone increases the maximum temperature rise, as expected. Also, lower pore fluid pressure leads to larger temperature rises, since the shear stress on the fault is greater. However, I found that none of the characteristics of earthquake cycles change with changes in W, the shear zone, frictional shear zone width. So even though the magnitude of the temperature rise appears substantial, it's so short-lived and so localized around the fault that it doesn't alter the overall behavior of the system at all. In fact, it's sufficient to use the steady state thermal anomaly, holding the temperature constant, to capture the earthquake cycle characteristics of the system. This is a comparison between a cycle simulation with shear heating on the top row and an equivalent cycle simulation without shear heating on the bottom row. The bottom simulation is the same simulation that I went through in the previous section. In contrast to the simulation without shear heating, very little aseismic fault slip occurs in the simulation with shear heating. So you can see the fault is dark blue almost everywhere here. This is because the brittle-ductile transition is so shallow that almost all the tectonic plate motion is going into bulk viscous deformation. As a result, the shear stress peak that produces the earthquakes is much more distributed. And the recurrence interval is quite different between these models. In the one with shear heating, the recurrence interval is 360 years, while in the one without shear heating, the recurrence interval is 270 years. So in this particular case, the inclusion of shear heating leads to a very different interseismic period, as well as very different earthquake cycle characteristics. Here I've summarized the effects of varying the geotherm and including shear heating on the depth of the brittle-ductile transition and the depth of earthquake nucleation and down dip propagation of the earthquake. I'm plotting the LAB depth on the x-axis and depth on the y-axis. Warmer geotherms correspond to a shallower brittle-ductile transition depth. Oh, sorry, shallower LAB depth. The figure on the right is for simulations with shear heating, and the figure on the left is for simulations without shear heating. The BDT, which I've defined as the range over which the fault accommodates 10 to 90% of tectonic plate motion, is plotted in yellow. Warm geotherms correspond to a shallower BDT, and shear heating produces a much shallower BDT. The down dip limit of the earthquake is plotted in blue. In most of the simulations without shear heating, so that would be this one, it occurs at about 16 kilometers. A little bit below the velocity weakening to velocity strengthening transition on the fault, which I've shown here in gray. And again, that's been fixed to be independent from the geotherm in these simulations. So in these cases, the brittle-ductile transition is very deep, and it's the velocity weakening to velocity strengthening transition that limits the propagation of the earthquake. But in the case of the warmest geotherm here, the BDT overlaps with the velocity weakening to velocity strengthening transition, and it shallows the down dip earthquake propagation limit just a little. In contrast, in the ones on the right, the ones with shear heating, the simulations, as you can see, the brittle-ductile transition occurs shallower than that velocity weakening to strengthening transition for all of the simulations. And as a result, it's the BDT that limits the down dip propagation of each earthquake. In addition to performing earthquake cycle simulations, I also developed an iterative method to solve for the steady state of the system in which earthquakes are neglected and the fault slips steadily at the tectonic loading rate. I use this method to compute plausible initial conditions for the earthquake cycle simulations, because without it, the spin-up period for the system to become independent from initial conditions is on the order of millions of years. However, it also turns out to produce a surprisingly accurate estimate for the brittle-ductile transition. The BDT, which results from the earthquake cycle simulations, is shown in yellow here, and the steady state approximation to it is shown in black. Furthermore, this estimate for the BDT can be used to estimate the down dip limit of coseismic slip as well, without needing to actually simulate the full earthquake cycle. Here I summarize the dependence of the recurrence interval and the earthquake size on the LAB depth. I find that the elastic simulations and the viscoelastic simulations without shear heating produce essentially the same recurrence interval and earthquake size. In contrast, viscoelastic simulations with shear heating can lead to much longer recurrence intervals, potentially almost 2 times as long. And though you might expect longer recurrence intervals to mean larger earthquakes, that's not the case. In some cases, the earthquakes are larger, and in other cases, they're smaller. The reason why the earthquake cycle characteristics are sometimes affected by the inclusion of a shear zone and sometimes not can be understood by looking at the shear evolution of the shear stress on the fault. These lines are shear stress contours plotted every 50 years through the interseismic period for an elastic simulation on the left, a viscoelastic simulation without shear heating in the middle, and a viscoelastic simulation with shear heating on the right. In the elastic case and the viscoelastic case without shear heating, there's a region of the fault beneath the seismogenic zone, which has approximately the same strength in both of these here, and that's slipping aseismically during the interseismic period with negligible viscous flow occurring. As a result, the evolution of the shear stress in this portion is the same as in the two simulations, and the seismogenic zone above this behaves in the same way, and thus the earthquake cycle characteristics are the same. With shear heating included, however, the brittle-ductile transition is shallower, almost no aseismic fault slip occurs, and the shear stress evolves very differently. And this leads to different nucleation depth and recurrence interval. So in conclusion, I found that shear heating produces a thermal anomaly on top of background geotherm, which weakens the root of the fault and shallows the brittle-ductile transition. The effects of transient shear heating are negligible for most simulations, and using the steady state thermal anomaly instead produces very similar results with a significant reduction in computational cost. Sometimes the presence of the shear zone does make a big difference for earthquake cycle characteristics, such as the recurrence interval, the earthquake size. And this occurs when the brittle-ductile transition is shallow enough that it impinges upon the seismogenic zone, which can lead to either larger or smaller earthquakes. And finally, I developed an iterative method to solve for the steady state of the system in which the fault slips steadily and the earthquakes are neglected, which provides an accurate estimate of the brittle-ductile transition and the down dip limit of coseismic slip propagation. And finally, I'll talk about work that I did during my postdoc at the University of Maryland with Laurent Montesi, incorporating the weakening mechanism of grain size evolution. Shear zones are characterized by reduced grain size and may deform in part through grain size sensitive diffusion creep. The results I've presented just far consider only grain size insensitive dislocation creep. Grain size evolution is the most widely preferred mechanism to explain shear zone localization and the changes in grain size and fabric commonly found in natural shear zones. And finally, it allows the model to connect with microstructural data from exhumed shear zones. My model includes both grain size insensitive dislocation creep and grain size sensitive diffusion creep operating in parallel. So the total viscous strain rate is equal to the sum of the dislocation creep strain rate and the diffusion creep strain rate. The dominant deformation mechanism is the one with the fastest strain rate. So as you can see from this d to the minus m term, that's the grain size raised to an exponent, the diffusion creep becomes relatively more important as the grain size becomes smaller. The time evolution of grain size is computed using the watt meter developed by Austin and Evans in their 2007 paper. Grain size increases through static grain growth, which is a thermally activated process. It's also dependent on the size of the grain. It's fastest for small grains and slowest for large grains. Grain size is reduced by work done through dislocation creep, with the coefficient chi determining what fraction of this work contributes to grain size reduction, the remainder being dissipated as heat. Austin and Evans suggest that chi is about 0.1, meaning that 10% of this work goes into grain size reduction. The watt meter equation can be solved for the steady state grain size when static grain growth and grain size reduction balance each other out. Solving for the watt meter's steady state grain size produces a piezometer-like relation. For a piezometer, the grain size is equal to the stress raised to the power n times a coefficient a. The watt meter result has the same functional form, but the coefficient a is temperature dependent, and the value for the stress exponent is a little different. So for example, for the TWIST 1977 piezometer for anorthite, the stress exponent is negative 1.47, whereas for the watt meter, it's approximately negative 1. On the left, I've plotted a deformation mechanism map for wet feldspar at lower crustal conditions. Here I've assumed 700 degrees Celsius. Stress is on the x-axis and grain size in meters is on the y-axis. The red section is where grain size sensitive diffusion creep is the dominant mechanism, and the blue is where grain size insensitive dislocation creep is the dominant mechanism. The purple line is the TWIST 1977 piezometer, the green line is the Post-Entellus 1999 piezometer, and the black line is the watt meter. All three predict that feldspar-dominated shear zones will deform primarily through diffusion creep. Here are my model's predictions for the structure of a fault and shear zone, including grain size evolution, using the steady state approximation in which the fault slips steadily, meaning there are no earthquakes, and the slip velocity, viscous strain rates, and grain size are determined as part of the steady state solution. This model is symmetric around the fault, so I'm showing cross sections on the right side of the domain with the fault on the left edge of the figure. The left figure shows the deviatoric viscous strain rate, and the right figure shows the grain size. To facilitate comparison between simulation results and different types of observations, Laurent and I developed 3 quantitative definitions of a shear zone. First, the kinematic shear zone, shown in red, is the region in which the viscous strain rate is elevated above 100 times the background strain rate from tectonic loading, or 10 to the minus 13 inverse seconds. Second, the deformation zone, shown in yellow, is a measure of the degree of localization and is defined as the region within which 90% of the total deformation occurs from both fault slip and distributed viscous strain. And third, the structural shear zone, shown in cyan, is the region in which the grain size is less than 50 microns, corresponding to the region within which myelinites might form. Using these 3 shear zone definitions, I consider the effects of grain size reduction and a concomitant switch to grain size sensitive creep. Here I compare the shear zone structure in a simulation without grain size reduction on the left, so where dislocation creep is the only active mechanism, with a simulation with grain size reduction on the right. In this case, grain size reduction shallows the BDT by 13 kilometers, but it has little effect on the shape and size of the kinematic shear zone and the deformation zone. My results suggest that while grain size reduction and grain size sensitive flow can have a moderate localizing effect, it may not be powerful enough to produce a highly localized shear zone. In this case, grain size reduction would be a consequence of localization, but not its cause. I also explore the effects of varying the tectonic plate velocity over an order of magnitude. The figures on the right are the viscous strain rate and grain size results for a high tectonic plate velocity of 10 to the minus 9 meters per second, or 32 millimeters per year, comparable to the San Andreas Fault in Southern California. The figures on the left are for a lower tectonic plate velocity of 10 to the minus 10 meters per second, or 3.2 millimeters per year, comparable to the Elsinore Fault in California. These encompass the range of plausible strike slip fault velocities. Higher tectonic plate velocity leads to a higher strain rate. This produces a deeper brittle-ductile transition and deeper onset of the shear zone. It also decreases the grain size by about a factor of 2. Interestingly, if I scale the strain rate from each simulation by the loading strain rate, which is the tectonic plate velocity divided by the domain size, then the resulting scaled viscous strain rate is virtually identical between these 2 simulations. So the kinematic shear zone and the deformation zone, the red lines and the yellow lines, are insensitive to changes in the tectonic loading rate. During the motivation, I told you that one of the advantages of earthquake cycle modeling is that the model results become self-consistent and independent of the modeler's potentially poor choice of initial conditions. This is true for elastic cycle simulations, which typically have a spin-up period of about 3 earthquake cycles or a few hundred years. This doesn't hold true for cycle models with viscoelastic deformation. For instance, spin-up time for a viscoelastic cycle simulation is on the order of millions of years. It scales with the Maxwell time, the ratio of the effective viscosity to the shear modulus, which is the characteristic timescale for a viscoelastic material to respond to a change in the system. The Maxwell time ranges over hundreds to millions of years in the lower crust and upper mantle. Similarly, the timescale for the diffusion of heat, relevant for systems with shear heating, is on the order of 10 million years, and the timescale for grain size evolution, plotted on the right here, is in the upper mantle, comparable to or shorter than the length of a typical interseismic period for large earthquakes. But in the lower crust, the timescale for grain size evolution in this figure rivals the age of the universe. So unlike for elastic cycle simulations, these very long spin-up times reflect real physical processes and are comparable to or longer than the likely lifetime of strike slip faults. Thus, this leads to the conclusion that fault and shear zone systems are not operating at steady state, and that to understand the fault and shear zone system, we need to move away from the assumption of steady state and consider the effects of inherited structure. To explore the temporal evolution of a fault and shear zone system, I perform time-dependent simulations in which earthquakes are neglected, and instead the fault slips aseismically up to the tectonic plate velocity. To focus on the crust here, I'm modeling only wet feldspar. These are snapshots of viscous strain rate in the top row and grain size in the bottom row at selected times. The initial conditions, the leftmost column, are the steady state stresses and strain rates consistent with constant 1 millimeter grain size. Under these conditions, dislocation creep is initially the dominant deformation mechanism, and appreciable viscous strain occurs only below 20 kilometers depth. Within the first year, the grain size near the fault drops rapidly where the work due to dislocation creep is the largest. This causes the dominant deformation mechanism to switch to diffusion creep within the shear zone. It also weakens the crust, causing a region of elevated viscous strain to form as well. Over the next 10,000 years, the shear zone, as defined by the viscous strain rate, slowly begins to localize. The layered grain size structure that's present far from the fault in the steady state result develops. This is contrary to my expectations going into this project. Also, using the simulation results, I can plot the evolution of the BDT over time. Here I'm showing the evolution of the shear stress on the fault over time. Time on the x-axis is plotted on a logarithmic scale, and depth in kilometers is on the y-axis. The color shows the magnitude of the shear stress, and I define the BDT as the depth at which 10% of tectonic loading is accommodated by slip on the fault, because as I showed in the shear heating section of this talk, this is a good estimate of the down dip limit of coseismic slip for large earthquakes. The evolution of the BDT over time is well fit by a line in log time, and I've plotted this line in cyan, and I've plotted the steady state BDT in orange. Extrapolating the cyan line predicts the steady state will be reached in 10 to the 11 years. Again, that's longer than the age of the universe. A young strike slip fault might be on the order of 1 million years, and a mature strike slip fault more on the order of 20 to 30 million years. This simulation without earthquakes provides an estimate for the down dip limit of earthquakes. To explore how earthquake size and recurrence interval changes as the system evolves, I'd like to do earthquake cycle simulations using time slices from this simulation as initial conditions. So to sum up the findings in this section, I found that grain size evolution is a significant weakening mechanism, potentially shallowing the BDT by more than 10 kilometers. And to facilitate comparison with observations, Laurent and I developed 3 definitions of a shear zone: the kinematic shear zone, representing elevated strain rate, the deformation zone, representing localization, and the structural shear zone, representing grain size. My results suggest that while grain size reduction and grain size sensitive flow can have a moderate localizing effect, it may not be powerful enough to produce a highly localized shear zone. And in this case, grain size reduction would be a consequence of localization, but not its cause. And finally, the stresses, viscous strain rates, and grain size in the vicinity of a fault may not be well represented by the assumption of steady state. The discrepancy between steady state and actual state is largest in the mid-crust, where relatively cool temperatures mean that the timescale of grain size evolution is very long. At the same time, this region's proximity to the base of the fault means that it may have significant implications for the earthquake cycle behavior. And I'll close finally with a quick description of my current work and some work I have planned. Right now I'm a postdoc at UC Davis, and I'm working on implementing earthquake cycles into Pilith. Pilith is an open source code widely used within the community, and it supports 3D simulations and complex fault geometry. So I plan to use it to investigate how realistic fault geometry and perhaps even multiple faults affect earthquake cycles. The long-term vision with this project is to develop an earthquake cycle code, which could be used to validate earthquake simulators like RSQSim. I also have a current project funded by a SCEC grant to explore the effects of dynamic weakening mechanism flash heating on viscoelastic earthquake cycles. And finally, I have an upcoming collaboration recently funded by the NSF with a geology group at University of Wisconsin-Madison to study the evolution of the Morin shear zone in Quebec, Canada. And with that, I'll take questions.
Great, thank you so much, Callie, for that wonderful talk. This is a great overview of earthquake cycle modeling and some of the important physical parameters in physics that we need to consider when studying earthquake cycles. If you have any questions, please go ahead and type them into the chat. If you prefer, just turn on your video camera and raise your hands, and we'll get to your questions then. While we are waiting for questions, just some reminders. Our next webinar in this series and our last of the year will be on, I believe that's May 12th, by Robert Walker, who's at SUNY Buffalo. He's also currently working with the Pilith group. Hopefully we'll hear about some of that work as well. We also are upcoming a special webinar series that will be starting soon on seismic cycles. So please look for that starting sometime in May. Okay, we have a question. Brad, go ahead.
Yeah, the implication, I'm wondering what your thoughts are on the implications of the non-steady state, and how do we then try and model things where we don't know the beginning state or have trouble assessing the current state? How do we assess the current state, I guess, is sort of the question then, if it's not steady state?
That's a great question. I'm not sure. I mean, so I want to say first that this is not a great representation. Like the initial condition I chose here is not something I would choose to represent an actual fault, because it doesn't pop into existence and suddenly start deforming. So I'm not sure. I think it's really challenging. I mean, it's exciting, but it's a real challenge to try to figure out how to actually deal with this kind of result. I think in the mantle that it's much less important, but it's really the lower crust where this becomes a problem.
Great. If there's no follow-up, I see a hand, Young Fei.
Hi, Kelly. Can you hear me?
Yes.
Yeah, great. It's a really great talk. It's very a lot of materials. So you went through from your PhD to postdoc. So my question is, basically, I guess the last slide you're showing for like mature fault, or the green side will be decreased. Then you show your the down dip limit will become shallower and shallower. So yeah, this one. So my question is, do you have some like observational support to say, okay, so for the mature fault, like the interest fault, they're going to have a shallower seismogenic depth, then we'll, because it's very important for future hazard evaluation, right? So do you have any like other support to observational, like geologists and evidence to support this?
No, I mean, I suppose this is something that we could go looking for, but the hurdle that I always run into here is that you know, everything's existing at its own temperature, its own history. And in particular here, I picked a pretty simple initial condition where you go from no grain size evolution to suddenly grain size evolution is dominant. And that's probably not representative. So I guess this piggybacks on Brad's point that we would need to do some real work thinking about what a realistic initial condition is to have the system evolve. Like, would we perhaps want to look at, I guess one I was thinking about is in the Salton Trough, where I believe the geotherm has been getting warmer with time. And so we could start at a cooler geotherm and heat that up and see what the effect is. And perhaps we could get something out that we can somehow match with observations.
Got it. Thank you. So my second question is about your the shear heating part. So you mentioned the shear heating effect, but at the same time, when you have shear heating and there's some dynamic weakening effect, like thermal position, that will like kind of lower the normal stress to reduce the shear heating level. Is that possible to kind of have compromise effect to you turn on the shear heating, but at the thermal position that will eventually we got like no, because you know the shear heating anomaly in Southern California. Is that possible, or still thinking the shear heating?
Well, it's an interesting question. So I didn't include any dynamic weakening like thermal pressurization during the earthquake, and the effect that that's going to have, first of all, is to decrease the amount of frictional heating. I don't think I put any figures in here, but I did do a lot of work where I just turned off frictional shear heating as a very rough proxy for that. But the problem is what that doesn't include is that when you have something like dynamic weakening, it changes the stress on the fault. And that, like, I think in particular, it allows much of the fault to operate at a lower stress on average throughout the interseismic period. And that will have a huge impact on the structure of the shear zone. So I think that really needs to be tackled as its own problem. One effect you might expect to see out of that, though, is a much lower thermal anomaly, which would be good because we don't really see strong evidence of a big thermal anomaly outside of faults. So I would expect to see that this should really bring down these numbers and change the shear zone structure.
Thank you.
Okay, any more questions for Callie? If there are no more questions, perhaps we wrap up a little early. Again, a few reminders that this webinar is being recorded, so look for it being posted shortly if you know of anybody who missed it who wanted to attend. If you're also interested in this topic and interested in modeling with the code pilot, we will be having a workshop in June in Golden, Colorado. That's quickly getting filled up. So if you're interested, please register as soon as possible. And you can find those links on our website at geodynamics.org. And once again, if you're not signed up for a community forum, and again, this topic is of interest, please look for our special seminar series that will be occurring late spring and through the summer on seismic cycles. So thank you once again, Callie, for a great talk. And we look forward to more great work from you.
Thank you.